Okay, let's have a look at question number 10. This looks a bit tricky because it's got a nasty looking diagram, but it's forces, it's got a pivot. The pivot should make you think moments, levers. It's got a spelling mistake, but never mind. Okay, that should be lever. And again here, it should say lever. But that you shouldn't throw you. Okay, so we've got a force, we've got a distance from a pivot, we've got another force. Tension is just a force, it just happens to be the force in the cable, and another distance. So the diagram shows a brake lever which has been pulled with a force of 35 newtons. So somebody's got their hand on it and pulled it like that. When that happens, the pivot here, it will turn around the pivot, it will pull the cable, and there will be a pull tension in the cable. Okay, calculate, first part, calculate the moment of the force applied by the cyclist about the pivot. So this is the force applied by the cyclist. We want to find the moment, and it's about this pivot, which is just saying that's where it's going to rotate. So I need my units and my equations. So go back to the equations. Okay, obviously you will have to remember some of these, but at the moment we've got them. Moment equals force times distance normal to the direction of the force. That means perpendicular. Okay, so force times distance normal to the direction. That's the force times the distance, and that distance there is at right angles to the force. The force is that way, the distance is measured that way, so this is a right angle. So our distance is okay. So moment equals, I'm just going to write it down, force times distance. Okay, and we're going to want to do it so that we need to give you the unit as well. So we need to remember what units we're using. So I can put 35 newtons times 110 millimeters. And if I wanted, I could just leave that and I could do 35 times 110. Let's just do that. 35 times 110 is 3850. And it is newtons times millimeters. So it would be Newton millimeters. But if I want to make it in standard units, let's redo it. Okay, it'd be 35 newtons times, well, 110 millimeters. In meters, there are 1,000 millimeters in a meter. So I have to divide that by 1,000. So I end up with 110 divided by 1,000, which is 0.11 meters. 0.11 meters. Okay, so if I do 35 newtons, which is the force, times 0.11 meters, which is the distance, I get 3.85, and this time it is newtons times meters, Newton meters. So either of these I can put down. I'm going to put down this one because it's the proper unit. Okay, 3.85 Newton meters. Note that I've multiplied newtons times meters. It's not newtons divided by meters, so it's not newtons slash meter. It's Newton times meter, which is Newton meters. Technically, although Newton meters and joules are meant to be the same thing, because this is not force times distance in the direction of the force, you can't write this as joules. Okay? If it was work done, you could write it as joules, but you can't write this as joules. You have to write it as Newton meters. Okay? Then, calculate the tension in the brake cable. It says assuming the weight of the lever can be ignored. Okay, so that just basically means treat this as a very simple question. Calculate the tension in the brake cable. Well, it's very much like this one here. We've got a force times a distance has to be balanced by a force times a distance turning the other way. So our person pulling the brake is turning the hand lever that way. The tension in the cable is trying to turn it that way. So I have a force, tension, times 25 millimeters has to equal the force this way, 35 newtons, times that distance, but in the same unit, 110 millimeters. Okay, I could convert them both to meters. Maybe I'll do that in a minute. Okay, 35 times 110 was 3,850, because I did that just there. I don't need to do it again. 3,850. Tension times 25 is 3,850, so tension equals 3,850 divided by 25, and that is 3,850 divided by 25 equals 154. 154. And it says newtons, okay? So it's got newtons, that's our answer. If I'd done it instead, and I'd done in meters, then I would have had 35 times 0.11, which is 3.85, is the same as tension times, well, 25 millimeters is 0.025 meters. Let's check that. 25 millimeters divided by 1,000 is 0.025 meters. So I would have had 3.85 divided by 0.025. Let's just check what that gives us. 3.85 divided by 0.025 equals 154. Surprise, surprise. It's the same answer because it doesn't really matter. As long as we're balanced, I can use millimeters on both sides or I can use meters on both sides. 154 newtons. Now, if we assume the brake cable has a spring constant of this and the tension that we calculated in A2 is correct, which means if you didn't know what your answer was here, if you wrote down 100, you could use that in the next one. If you don't know how to work this one out, just write down something here because you're going to need to use it and write an easy number like 100. What would the extension of the brake cable be in centimetres? Okay, this is going to be a trick at the end. We'll work it out firstly in metres because we've got our answer for the spring constant is in metres and this is in newtons. So everything's going to be in newtons and metres to start with. So we look for our spring constant equation and the tension is just a force. So our force is the spring constant times the extension. So force equals spring constant, which is K, times the extension. To rearrange that, I've got E equals F divided by K. All I need to do then is put my numbers in, remembering that my answer is going to be in meters. So I have F, which is 154, divided by 13,900. Okay, it's going to be 154 divided by 13,900 equals, and that is 0.011079 something meters. Okay, so my answer is going to be in meters because it says newtons per meter and this is newtons. To get that into centimeters, well, if it's 0.01 meters, to get centimeters, there's 100 centimeters in a meter, so I've got to multiply by 100. So I times that by 100, and I get, so times by 100 gives me 1.1079 blah centimeters. But I probably shouldn't give that many significant figures because I've only got 3 significant figures here. I'm going to put it as 1.1, maybe 1.11 centimeters. Okay, but 1.11 centimeters. Note what happens if you accidentally get this the wrong way up. Okay, if you accidentally do this the wrong way up, 13,900 divided by 154, we would get 90.25 meters. Just think when you're doing this, would that answer sound correct? If I pull on a brake lever, is the wire that connects to the brakes going to get longer by 90 meters? And that doesn't sound right to me. Okay, so that would tip you off that maybe you've made a mistake and you flipped it up the wrong way. Okay, the last part. Okay, use your answer to this. Again, if you couldn't work this out, you could put something in here, okay, and use it to calculate the elastic potential energy stored in the brake cable. Well, the elastic potential energy is another word for the energy in the elastic store in a stretched spring or a stretched piece of wire or something. Okay, so we need to look for an equation for that. And actually, this is one that you would get given. Energy transferred in stretching, which is the amount of energy that would be stored in the wire when you stretch it, is 0.5 times the spring constant times the extension squared. Note the squared. And we've got spring constant and we've got extension because we just worked it out. So we can find that. So I'm going to write down energy equals 0.5 times the spring constant, which is K, times the extension squared. Remember, though, that we have to make sure that we're in the correct units. This is 1.1 centimetres, which is 0.011 metres. So I have to be in metres to work it out properly. Okay, so that's 0.5 times K, which was this, 13,900, times the extension, which is 0.011079 squared. Okay, because that has to be in metres. And that is 0.5 times 13900 times, I'll put it in brackets, although it would work without, 0.011079 squared equals 0.853 joules. And that will do, 0.85 joules.